Today we are going to study the introduction to nuclear radiation detectors. So, what is meant by that? So, we are studying about nuclear radiation detectors. Okay, so why do we need radiation detector? So much of what we know that today about the structure, properties and behavior of atomic nuclei from experiments. So we know the properties by experiments. Okay. So the properties and behavior of atomic nuclei comes from experiments. So in this experiment, we observe radiations and particles emitted from the nucleus. These emissions carry important information about the nucleus itself. So some nuclei are naturally unstable, that is, and emit particles or radiation. Other nuclei can be made unstable by bombarding them with the energetic particle. So there is two types of nuclei, the unstable and stable nuclei are there, but can be made unstable by bombarding them with the energetic particles. So studying these radiations help us to understand the nucleus. Okay. So why the need for detection? Okay, the radiation emitted by nuclei are very tiny and invisible to our senses. Okay, human senses are not recognizing this radiations. Okay, radiations we have to detect that, but humans are not capable to this for detection. So that artificial devices we need for radiation detecting, that is called radiation detector. So we need radiation detectors. Okay, radiation detectors we need. And also we know that by modern physics we know that the particles like electrons, protons and neutrons, which are particles but they behave like a waves, that is particle wave duality, we know that. And also waves which exhibit the properties as particles. Okay, so the particles and waves that both that is called the particle and wave duality. So the particles like electrons, protons and neutrons can behave both like particles and waves. Okay, this is called the dual nature. For instance, we know that electrons exhibit diffraction. So electrons, we know that is particles which show diffraction, which is wave behavior. We know that that is wave behavior. Okay, that wave behavior, wave phenomena is shown by that electrons. And also light also shows that wave also it has a particle behavior. Okay, that is example photoelectric effect and Compton scattering. So light, we know that there is a light photons, that is wave behavior, but they show photoelectric effect. Photoelectric effect and Compton scattering. Okay, next we know that because of this we have to commonly use particles or electromagnetic radiations. These two are commonly used as radiations because they shows that particle wave duality character. So we can both particles and radiations by common name radiation. Okay, particles is also called as a radiation. So basic principle of radiation detection is that relies on interaction. Okay, the basic principle. The basic principle in which we have to know that when a radiation passes through a material means the active medium inside a detector, it interacts with the atoms and molecules of the nuclei of that material. Okay, so when an interaction, when a radiation comes to that, passes through the material, so we have to draw a plot like this. When a radiation comes to the material medium, active medium, that is detector active medium, such as maybe gas, liquid or solid. There is some interactions occur with the atoms, molecules or nuclei of that material and create ion pair. So this interaction creates ion pair. Okay, so this will create ion pair. Okay, so ion pair, we know that when a radiation interacts with the atoms or molecules inside this active medium, it creates ion pair, that is positive ion and a free electron. Positive ion or free electron. So we know that electrons are negative and positive ions positive. So there is an electric field inside the detector to collect these ions. The electrons are attracted to the anode. That is anode is, we know that is a positive electrode, and positive ions collected to the cathode. It is negative electrode. So the movement of these charges, create a electrical signal, which is measured and analyzed. This is measured and analyzed. By this we can measure the radiation. Okay, in a detector. So the active medium we used inside the detector, this active medium, which may be gas, liquid, may be solid. Okay, so gas detector is first type of studied because early scientists observed that the radiation ionized by air. Okay, gas detector. Liquid detectors also used, and solid state detectors, in which we know that the silicon detectors is an example. So these are the detectors there. Okay, so we studied about the radiation detectors. So the two features we have to know, chief features of detector. We have to study that chief features of detector. Sorry. Okay, what is the chief features for the detector, radiation detector? One is energy resolution. Energy resolution. Okay. Second is detection efficiency. So the energy resolution and detection efficiency is very important for a radiation detector. It is very important, energy resolution and detection efficiency. The detector resolution. Well, what is the purpose of a detector? So what is the purpose of a detector? That is, it is convert the so first of all we have to find the what is meant by energy resolution. Okay, energy resolution. So we know that there is an electrical signal is created. So in a detector, it is to convert the energy from incoming radiation into a measurable electrical signal. Okay, the energy can be measured from the electrical signal. but the conversion process is not perfectly smooth. Okay, it happens through several steps that are random in nature. So for example, when a radiation enters to the active medium, it generates charge carriers. We saw that is free electrons and positive ions can be created by the interaction of atoms and molecules present in the active medium. So the number of charge carriers is not exactly same each time, even if the same radiation energy enters. Hence the output signal fluctuates slightly. So the other problems like detection noise or drifts in detector, slow changes, behavior can also cause fluctuation. So this is not the energy resolution. Here we said about that there is we know that that electric signal created by the same energy itself, maybe there is some fluctuation in the electrical signal, there may be some problem. Also detection noise is the for to know the energy resolution, we have to study about the pulse height spectrum. So if you imagine that is a collecting signals from your detector, if everything were ideal and you were detecting the radiation of one single energy, you would expect that all the signals to be at the same height. Okay, that is all pulses would have a same voltage, but because of statistical fluctuation the height spread out a little. So the number of pulses versus pulse height, you get a not a sharp line, you get a curve. Okay, so that is called a pulse height spectrum. So we know that when interaction occurs, there should be some electrical signal corresponding to some energy. Okay, so if you are detecting one single energy, you are expecting some sharp line. Sharp line means that voltage should be same. You are the pulse height should be same. You are expecting that, but there is some fluctuation in the voltage, and there is the number of pulses was the pulse height. Number of pulses was the pulse height should be different. The pulse height maybe shows like this. Number of pulses, number of pulses, pulse height. There may be some spectrum. So instead of a sharp line, you are expecting the pulse height, the number of pulses. So in this condition we are measuring one single energy. So we are expecting one single output with the constant voltage, same voltage, but there may be some fluctuation. So that the number of pulses versus pulse height, we are expecting like a sharp line, but we are getting the pulse height is different and we are getting a spectrum. So that is called the pulse height spectrum. So where the pulse height spectrum. So in this figure we show that the peak occurs at a voltage V0 corresponding to the most probable pulse height. So we are drawing this graph like this, that is number of pulses, pulse height. So we are getting like this. Sorry, there is some like this spectrum we will get. So at some particular voltage we are getting most of the pulses, we are getting this. Okay, so this is the most probable pulse rate. The voltage is called V0. The peak has a finite width, not zero. Okay, the width of the peak is measured at the point where the pulse height is half. When the pulse height is half, and where we have to find the width. So that is called a full width at the half maximum. The maximum and it's a half and find the full width at the half maximum. That is called as FWHM, and it is represented by a symbol tau. So not tau, gamma. So the narrower the peak, peak should be narrow, the smaller FWHM. Okay, FWHM will be narrow, a small for narrow peaker, and for broader peaker it should be like this. Okay, so for a better detector, that FWHM will be narrow, small, that peak should be narrow, because we are expecting some like a sharp line for a single peak, but we are getting a spectrum because of some fluctuations. So FWHM is small means the peak should be narrow, that is for better energy resolution, but the peak is broader means FWHM is very big and also the resolution is worse. Okay, so you get the idea of FWHM and a resolution. I think about this like that. So FWHM helps to understand how well your detector can separate two nearby energies. So resolution is once again can be get from FWHM. So the resolution means that to separate two nearby energies. Okay, separate two nearby energies. So if your two gamma rays have very closely energies, a detector with a good resolution means that good resolution means FWHM small, it is very low, and can detect separate peaks. So for two different energies, two gammas can be detected like this. Okay, if it is the resolution is very poor, that peak should be maybe merge like this. So you cannot distinguish the two gammas. The energy resolution of the detector depends on its FWHM. So better detectors have smaller FWHM, and for that better energy resolution. Okay, so the resolution can be quantitatively defined as resolution R is equal to gamma, we know that FWHM, divided by V0. V0 is the pulse height corresponding to the peak. Okay, so that voltage pulse height corresponding to that peak, that is V0, and full width at half maximum gamma. So resolution we will get like this. So we know that we can compare that detectors, sodium iodide detectors. We know that sodium iodide detector, NaI detector, and HPG detector is the, and surface barrier detector. Okay, surface barrier detector. So radiation they are detecting, that is sodium. This is surface barrier detector. So sodium iodide we know that is gamma rays, for HPG is gamma. Surface barrier detector for alpha. So typical energy, energies for that 1 MeV it is measuring. So for that FWHM is 70 for sodium iodide, 2 for HPGE, and surface barrier detector is 14 for FWHM gamma. So we know that FWHM is very small means resolution is very high for HPGE detector. So in R is percentage wise, that is R percentage, that is 7, 0.2, 0.28. So HP detector has excellent energy resolution compared to the detector, sodium iodide detector. That's why HPG detector are widely used when precise energy measurements are needed. Okay, the detector resolution is very good. Okay. Next, sorry, here is their typical energy. That range for this is 5. So by this is V0 typical energy. So by finding this R by using the equation, we will get a resolution like this. So we know that here the resolution is more for HPG detector compared to sodium iodide detector. Next chief feature is for the detection efficiency. So detector efficiency. So detector efficiency, another crucial feature of detector. When radiation hits the detector, some of the radiation is detected. Okay, interacts and produces a signal. Some radiations pass through without interacting. So we know that some active medium and when interaction is when radiation is coming, there may be interaction, but some of the particles or radiation we can commonly called as radiation, we said like this. So the radiation cannot be without interacting, they passes. So thus not every radiation particle or a photon is detected. The fraction that is detected is called detector efficiency. So there is a types of efficiency detector, that is absolute efficiency is the absolute efficiency is termed as epsilon absolute. Okay, so the number of output pulses recorded divided by number of radiation quanta emitted by the source. So the number of, that is termed as the number of output pulses recorded divided by number of radiation quanta emitted by the source. So output by input, radiations emitted by the source. It depends on the properties of detector and the geometry, the distance between source and detector size, and also the solid angle. How much the emission sphere the detector covers is also matters. The efficiency depends on these things: the detector and source distance and detector size and also solid angle. Okay, so what is meant by absolute efficiency? The number of output pulses recorded divided by number of radiation quanta emitted by the source. Another is intrinsic efficiency. Intrinsic efficiency is the number of output pulses recorded divided by number of radiation quanta incident on the detector. That is not emitted by the source. The number of radiation quanta incident on the detector, that is intrinsic efficiency. Okay, epsilon intrinsic, that is number of output pulses recorded divided by number of radiation quanta incident on the detector. Okay, so it only depends on the detectors on properties. It does not depend on the geometry or solid angle. Okay, all these depend on in absolute efficiency. For intrinsic, it depends only on the detectors and detector properties only. Solid angle, it does not depends upon the solid angle. So what is the relation between epsilon intrinsic and epsilon abs? Okay, So the intrinsic efficiency and absolute efficiency, what is the relationship? So that is intrinsic, that's equal to that is for isotropic source. Isotropic source, that is equal emission in all direction, that is intrinsic efficiency is equal to epsilon efficiency into 4 pi by omega. So omega is the solid angle subtended by the detector at the source, and if the detector covers more solid angle, if the detector covers more solid angle, absolute efficiency is become larger, but epsilon intrinsic stays same because it is independent on the of the geometry. Okay. So the resolution we studied about, that is the ability to distinguish both the closed energies, depends on FWHM. Absolute efficiency, the ratio of detected pulses to emitted quanta, depends on the geometry, solid angle. For intrinsic efficiency, the ratio of detected pulse to the incident quanta, that is independent on the geometry. Okay, intrinsic, it is independent on the geometry. Next, we have to compare about the charged particles and photons. So the charged particle interaction is with the matter. In the case of charged particle, the interactions with the matter is characterized by the quantity dE by dx. dE by dx is the stopping power. So we can write charged particle. For charged particle, the interaction, the charged particle loss continuously as they move through the matter. So when it is moved through the matter, it continuously loses energy. The energy lost per unit length is called stopping power, that is dE by dx. Stopping power, it is very important. That is energy lost per unit length. Okay, dE by dx. Since they interact so readily, even a thin detector can stop charged particle. Okay, thin detector is also stopping the charged particle. The detection efficiency for charged particle is usually very high. Okay, the detection efficiency is for the charged particle, it is very high, around 100%. But gamma rays and X-rays, the interaction is not continuous. It is not continuous. It is entirely different. Their interactions with the matter. Okay, it is probabilistic. That is, we can write as the gamma rays or X-rays. Entirely different interactions with the matter. Gamma rays may pass through the matter without interacting. Thus the detection efficiency is lower for photons. Okay, efficiency is lower. For charged particle, it is 100% around. So that so for gamma rays or X-rays the radiations, the detection efficiency is lower, and without interacting, maybe it passes through the material and matter, there is no interaction. So this property which give rise to an exponential variation of intensity of transmitted beam. So the transmitted beam, the beam intensity of the photon falls on a detector of thickness x. So if you are considering detector with the thickness x and the beam showing a variation like decreases exponentially, so the intensity I is equal to I0 e raised to minus mu x. So I is the transmitted intensity and I0 is incident intensity. Mu is the attenuation coefficient. X is the thickness of detector. So why it is showing the exponential behavior? Because there is some electromagnetic radiations like X-rays and gamma rays. They may be without interacting passes through, and maybe it is scattered away or it is completely absorbed. So that is removed from the main beam. So the transmitted beam showing an exponential behavior. This equation is I is equal to I0 e raised to minus mu x. That's the fraction of photons detector. So the epsilon intrinsic efficiency, that is equal to, we know that incident transmitted, that it is output, and divided by incident, that is equal to 1 minus e raised to minus mu x is the epsilon intrinsic. So high mu and large x means more absorption. Epsilon intrinsic, high mu is, we know that attenuation coefficient, and large x is the thickness of the detector, and which means more absorption, hence better detection. Okay, so high mu and large x means more absorption, hence better detection. If the source is not a point but spread out, or if the detector is a finite sized, the path length inside the detector vary depending on where the photons enter. So we need to integrate over for all paths. So epsilon intrinsic efficiency 1 by omega 0 integral 1 minus exponential of e raised to minus mu x d omega. So if it is not considering a point source and but is spread out, or if the detector is finite sized, so there may be difference in path length inside the detector, very depending where the photons enter. So we have to integrate over that, and d omega is the small solid angle element. So for low energy photons, attenuation is large, mu is large. So mu is large means efficiency is high, so almost 100%. If it is high energetic photons, attenuation is less, so the efficiency drops. For 1 MeV, gamma rays detection efficiency is about 25 to 30% detection. Larger detector size, if you are considering larger detector size, so x is more, that means efficiency is more. Okay, that is the conditions we studied. So we studied charged particle efficiency is about 100%. For gamma or X-rays with low energy means efficiency is very high. High energy means efficiency is low detection efficiency is there, and for larger detector size is greater, that means efficiency is high. Okay. So for gamma rays, the pulse height spectrum. Is characterized by main Gaussian peak called photopeak. So for gamma ray interact with the detector, ideally it should deposit all its energy and this produces a photo peak. But often only partial energy is deposited due to process like a Compton scattering. So thus the pulse height spectrum has a sharp photo peak, that is full energy deposited, and plus a broad continuum at a lower energies. Lower energies there is a broad continuum. So photo peak is the, and there is a lower energies there is a continuum. Okay, broad continuum is the. So the two types of efficiencies are that is total efficiency epsilon dot, that is photo peak efficiency, counts from all events. Epsilon dot is the total efficiency, that is from photo peak plus continuum. So why continuum? Why continuum means there is a continuum at lower energy deposited due to process like Compton scattering. So the total efficiency epsilon dot is equal to photo peak plus continuum, all events, that counts from all events is the total efficiency, and photo peak efficiency epsilon peak, that is from photo peak efficiency, counts only from photo peak. Okay, so there is a two efficiencies for the case of gamma. Okay, so the peak to total ratio, that is represented by R, that is equal to epsilon peak divided by epsilon total. So epsilon P, that is the photo peak efficiency divided by total efficiency. Just you have to go through it, or it's not that much important. It measures what it is happens, because here it measures how clean the photo peak. It is compared to the total recorded counts. Okay, if higher R means the spectrum is dominated by the true full energy. Okay, so then there is less contamination. So higher R means higher photo peak efficiency, that is the Compton scattering, that continuum is less. So higher R means it is dominated by true full energy events, so less contamination. Higher R means less contamination. Okay, so there is less scattered gamma rays. Okay, so in practice we usually use only the photo peak efficiency, because the lower energy continuum can have a lot of contaminations, that is scattered gamma rays from the walls, tables, etc. So photo peak efficiencies we are usually taking, epsilon total we are not taking, but we can find the peak to total ratio if there is less contamination, or how much contamination is there from that R. Okay, and also for neutrons the situation is somewhat similar to gamma rays. So what is case of neutron? Neutrons, it is also show exponential attenuation inside the detector. There is also exponential attenuation inside the detector, but neutron detection efficiency is not smooth, especially at lower energies. Resonances in neutron cross sections make efficiency irregular. This means at certain energies the interaction probability suddenly becomes very large, because there is some at lower energies there should be some resonances. So there is a cross section make efficiency irregular. So neutron detector efficiency curved are jagged at lower energies. Okay. So gamma ray smooth efficiency decrease with energies, but neutron's efficiency is irregular at lower energies because there may be some resonances. Okay. So these are the things we are studying in this chapter, the nuclear radiation detectors. We studied about the detector resolution and detector efficiency. Okay. So thank you.